Okay, starting on page 36. We got function 2 to the x squared. Select values of f are given. Approximate f prime of 0.5. So we just find the slope between the points to approximate. So change in y over change in x. But if we use our calculator, f prime of 0.5, our calculator will tell us it's 0.567. So it wants to know the difference between the approximation and the actual slope. We just subtract those two values. Morning, Maddie. 0.433. Okay, number 9, the graph of a trig function is shown below. At which of the following points could the instantaneous rate of change equal to the average rate of change on the interval from A to B? I think the closest is the instantaneous rate of change of B, or the instantaneous slope at B seems to be close to the slope between points A and B. So that's kind of the closest slope that we can find, right? Any other point feels like a different slope.
Mr. Yang, can you re-explain that one?
Yeah, because the average slope from A to B is a little bit on the downward slope, right? And that's close to what slope at B is. Slope at A is more of a slope 0. So slope between A and B is closest to the actual slope of B.
Okay, I get it now. Thank you.
Okay. Which of the following could be true? We have a bunch of statements about continuity and differentiability. So we know that the breaking point for these two graphs, potential breaking points, is at 2. Okay. So right now we know that these are two lines here at 2. Right, one has a positive slope. They both have positive slopes, but we just don't know. Are they connected and are they going to share the same slope? So what we can do is we can set the equations equal to each other, see if they actually arrive at the same y value, and then find their derivatives and see if their derivatives are even the same. Okay, so 3x plus 5. Sorry. So I can just, well, basically I just find f of 2 for both of these, but yeah, I can just set them equal to each other. If I solve for x, yeah, you're right. Because if I was just doing a shortcut here, because if I can plug 2 into both of these, and if they both give me the same y value, I know the limit's going to exist. But yes, you're right. I think I was skipping ahead to this differentiable statement here. But yeah, f of 2 will be 6 plus 1, which is 7. Approaching 2 from the left versus approaching 2 from the right. We get 7 on the left side. And then plug 2 in, we get 10 minus 3, which is also 7. And the point exists where the limit exists. So we know this is continuous. Now, differentiable would mean that they have the same slope. So if I find f prime, the derivative of 3x plus 1 is 3. The derivative of 5x minus 3 is 5. So it's a constant slope. One has a slope 3, the other has a slope 5. If I even though they're connecting, there's going to be a sudden change in slope, and that's going to make it not differentiable. Same slope. Gotta have the same slope. Otherwise, the graph will look like this, where there's a sudden change, and that sudden change is causing a sharp turn, and that sharp turn means not differentiable. Okay, got a limit problem here. First thing to do with limits is just go ahead and plug in the h, see what happens. Remember, h is the variable here. Okay, 0 over 0, that tells us we can find the derivative. Remember, you're finding the derivative with respect to h. So h is the variable here. Okay, we have to make the adjustment, and that x is the constant. Because it's h that's moving. That's the unknown value here. So if you want to find the derivative, 5e to the x, normally you would say the derivative of 5e to the x is 5e to the x because e to the u times u prime. But this is actually going to be just a number, so that's going to go to 0. 5e to the x plus h, in other words, imagine this is 5e to the 1 plus x, or 1 plus h. The derivative of this is going to be 5e to the x plus h times x plus h's derivative, and h will turn into 1, and 3h turns into 3. We got to make the adjustment here. H is the variable. So now I can reevaluate, plug the remaining h with 0. So we're left with negative 5e to the x plus 0 over 3, which is negative 5e to the x over 3. So L'Hopital's rule is all good and fine, but you have to make the adjustment that it's not x that's the variable, it's h that's the variable. We want to find f prime of 2, but to find the derivative, notice that these are two separate terms being multiplied together. We got to go through product rule. Okay, F prime. Remember, treat B like you would if it was just a number, like a 3 or 5 or 6. 5x's derivative is 5, so bx's derivative is just b. For what value of b is f prime of 2 equal to 0? So they're telling you what the x and y values, or they're telling you what the f prime value is. They're telling you what the x value is. So now the only thing left over is to solve for b. Okay. They tell us g of 2 is 3, g prime of 2 is -1, so we'll just continue cleaning up. Hopefully we can just isolate all the b's together here. All right, great. Copy this wrong here. X cubed eight plus 6 is 14. <clears throat> 36 minus 14 is 22. Okay. 13, we're given h of x, which is not shown, but h is built out of f and g. If you want to find h prime, we got to go through quotient rule. So f prime g minus f g prime all over g squared. Replace every x with 3. And then you're just interpreting, are you pulling the slope or the order pairs from each of the graphs of f and g? So the points in question are f of 3, g of 3, f prime of 3, and g prime of 3. F of 3 is the order pair, which is 4. F prime of 3 is the slope of this f graph and the slope of this line segment. Pick any 2 points. I can go up 1 over 2. That's my slope. G prime of 3, the slope of the graph at 3 is the negative slope. Pick any 2 points. I go down 3 over 1, so -3. And it's just a matter of plugging all these numbers in and getting it down to a numeric answer that matches the answer choice C. At 14, which of the following correct process for finding h prime of x? So we recognize this as chain rule here. Outside, oh, first here, show brackets to show the full outside here. So outside's derivative, h prime, is the 2 bracket to the first power. Multiplied by the inside portion's derivative. So 1 goes to 0, f of 3x becomes f prime of 3x. And finally, the innermost portion, 3x becomes 3. Okay, so g is some inverse function that we don't see in front of us. We know that the table that's going to help us find g prime. So the ordered pair that we see here is 4, 6. So I know that f of 4 equals 6. I know that f prime of 4. I can just pick any 2 points, find the slope of this curve. 1, 2, 3, 1, 2, 3, 4, -3/4. The slope of this line is the same as the slope of this curve at this point. So the slope of -4 is -3/4. And we learned about how the order pair for the inverse function is always going to be flipped. So instead of 4, 6, it'll be g of 6 equals 4. So therefore, the x value on the g side is 6, and the slope is going to be the reciprocal. Okay, 16 is a more traditional derivative inverse at a point. I want to find g prime of 2. I know 2 is the x value of my g function, which is also the y value of my f function, sorry. So if I can find f prime of 1, I can find g prime of 2. But it looks like, oh, sorry, f of -1 equals 2. So -1 is equal to 2. So I'm not able to find enough information to actually get to, if you look at the answer choices here. So whatever the slope I find here, I know it's going to be reciprocal. So it's going to be 1 over whatever the slope I find at f prime of 1. -1, sorry, keep saying 1. So here, I'm representing my answer in terms of whatever slope I get. Let's say if it was 3, it'll be 1/3. So whatever f prime negative 1 is, I'm going to flip it. On page 40. Yeah. Okay. Thanks. No problem. Okay, so y equals 2 natural log of x. We're asked to find the fourth derivative, so we'll just go through each derivative rule and see how far we can get. We know if we're starting off with y equals 2 natural log of x, y prime is simply u prime over u. So 2 natural log of x becomes 2 times 1 over x, right? X is my u value, u prime over u, 1 over x, the 2 stays. So y prime is really 2 over x, which is also 2x to the negative 1, just to get myself ready for my next couple of derivatives. Okay, so I can just do power rule for my remaining derivative, second derivative. Negative 2x to the negative 2. Keep going. Third derivative, 4x to the negative 3. Keep going. Negative 12x to the negative 4. Clean this up. Answer choice B. Figure above shows the graph of f prime, which is the derivative of f. At which of the 4 indicated values is f double prime the greatest? So f double prime is the concavity value. So think of f double prime is the slope of the f prime. Okay. So where's the slope of this f prime going to be at the greatest? This one looks like it's a positive slope of, maybe 0.5. This looks like a positive slope of maybe 2 or 3. Slope of 0, slope of negative 2. The largest one is going to be this one here. We're looking for the greatest value, so the most positive one. This may be a steeper slope, but in terms of largest, we're trying to head towards a positive direction. Okay, page 42. Let f be a differentiable function, so smooth curve all the way through. F of 0 equals -4, f of 10 equals 11, which of the following must be true for some value. So I see a bunch of statements about f prime, so I'm just going to go ahead and find the slope between these endpoints and see what I get. So changing y, we're changing x. So it's differentiable. I know that this is basically saying mean valley theorem, right? Whatever slope I get between the endpoints, I know there must be this exact instance of the slope somewhere along the curve. But I'm trying to figure out which of these is a better fit. This is not quite right. 11 plus minus 4 should be y2 minus y1 over x2 minus x1. So this one is a better fit, even though they both are referring to the same mean valley theorem. Okay, we have f of x. Of the following intervals on which can the mean value theorem be applied? Well, we know mean value theorem has to be on the interval where there's no sudden breaks, right? The whole function does not have to be continuous or differentiable, but at least for the interval, it needs to be continuous. So we know that there are some discontinuities along this graph. So we know that mean value theorem cannot cross over any of these x-intercepts. So we know there are vertical asymptotes at x equals 4. Set x minus 4 equal to 0, I get x equals 4. Set x plus 2 equal to 0, I get x equals negative 2. So I know that if I'm going to create any intervals, it's got to be around these asymptotes. It can't cross over these asymptotes. So my graph is only going to exist in these intervals from negative infinity to negative 2, negative 2 to 4, and then from 4 to infinity. Okay? Anything that crosses over the asymptote, we can't use. Okay, negative 1 to 3 is okay, right? It falls within this interval. It doesn't interfere with the asymptote. 5 to 7 is okay, right? Doesn't interfere with the asymptote. 1 to 5 is an issue because if I do 1 to 5, it's going to cross over 4, and it's not going to be fully continuous throughout the entire interval. So options 1 and 2. Okay, we have a continuous function shown. But notice it doesn't say anything about differentiability. So, all these points may be connected, but there may be some sharp turns. Which of the following statements could be false? It could be false. By IVT, there's a value there's a y value that is 10. That is true, right? If I start at 1, if I end at 31, I gotta reach 10 somewhere somehow, as long as the function is continuous, that IVT is true. By mean value theorem, there's values such that f prime is equal to 10. There's no mention of differentiability, so if it's not a smooth curve, mean value theorem can't apply. EVT applies if a function is continuous, and EVT applies if function is continuous. It's just the B that could be false because we don't have no mention of differentiability. Okay, the figure above shows the graph of f, which the following could be the graph of f prime. So I probably went a little bit deeper than what I needed to do, but I just wanted to sketch something that is as accurate as possible. So I just labeled a lot of these points with given letters, just so I can track my progress. So I know that whatever the peaks and valleys are, those are my peaks and valleys. So my sign line will look exactly like my graph, and my concavity will look exactly like my graph because this is my original graph. So I'm just picking some random points as potential points of inflection because I see a change in curvature around these points. So concave up, concave down, concave up, concave down, concave up. So how does that look from the f prime side of things? However many points of inflection I have on the original graph on the f prime, those will show up as peaks and valleys. So I'm looking for 4 peaks and valleys. I'm looking for 3 x-intercepts, right? Because I have a max, a min, and a max. So 3 x-intercepts, 4 points of, 3 x-intercepts, 4 peaks and valleys. And then once I drew out my graph, it looked closest to answer choice B.
That's because for the first f of the f graph, if it's going up the x-axis for the f prime going down the for the
Exactly right. So wherever there's a positive slope on the f of x graph, it has to show above the x-axis on the f prime graph, right? Right. So I labeled the positive, negative. I labeled the positive above and below, and I just sketched. I sketched the graph without looking at the answer choices, just so I can kind of build it from scratch, and then I matched it with my answer choice here. Okay, which of the following statements could be true? I have all these statements about horizontal and vertical tangents. That's referring to the derivative. So I have to find the derivative first. To find the derivative, I have to go through power rule and implicit, because I have y's all over the place. Oops, sorry. Divide both sides by 2y plus 16, get that dy dx by itself. I'm going to just try to clean up as much as I can, factor a 3 out. Okay, so there's my derivative. Now you see mentions of horizontal tangents. So horizontal tangent, you can find that by setting the numerator of the derivative equal to 0. Vertical tangents you can find by setting the denominator of your dy dx equal to 0, of your slope equation equal to 0. So if I want to find places where the slope is 0, I can look at the numerator. If I want to find places where the slope is undefined, I'll look in the denominator. So -2, tangent, horizontal tangent, that's true. Y equals -8, vertical tangent, that's true. And then the line has a slope of there's a slope of 1/2 at order pair -1, -1. So if I plug -1, -1, 1 in for x and y, I get 4 minus 1 is 3, 3 times 3 is 9. Plug 1 in here, 1 plus 8 is 9, 9 plus 2 is 18. So 9 over 18 is 1/2. I do get a slope of 1/2, so all 3 statements are true. Okay, so we'll pick up on page 44 this afternoon.